All right, let's look at questions 3 and 4. First, find all elements in Z10 which have multiplicative inverses. Now, the section in the book that refers to this is right here, multiplicative inverse for modular arithmetic. And let's see what the result is. All right, so here we go through a bunch of stuff. Now look here. Here it says, if P is a prime number, then all elements in ZP not 0 have an inverse under multiplication mod P. Now we don't have a prime number, we have 10, so that's not going to work. But that seems to show that primeness has something to do with the multiplicative inverse. So look at proposition 3529. Let n be an integer and let a be an element of Zn minus 0, non-zero element of Zn. Then a has an inverse if and only if the GCD of a and n is 1. That is, a is relatively prime to n. So how can we apply that in our particular situation? Well, n, our Zn, is 10. And we're looking for elements that have inverses in Z10. So I need only the numbers in Z10 that are relatively prime to Z10. So I'm looking for relatively prime. In Z10. So let's look at 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the candidates. Now, which ones are relatively prime? Well, 2 has a common factor, 4 has a common factor, and 2. 5 has a common factor, 6 has a common factor because they're both divisible by 2. 8 has a common factor. So 1, 3, 7, 9 is the answer. Okay. All right, let's go on to question 4. Let's see if I can move this up. I guess I can't. And so it says, compute the following, show your reasoning. Okay, I figured out how to move it up. Here it is. All right, so show your reasoning. Mod 4 to the n5, where n is an even number greater than 1 million. All right, so for 4a, and I think a lot of people did this, which is good. So you try n equals 1, 2, 3, 4, 5, and then you took mod 4 to the n 5. If you take n equal 1, mod of 4, 4 mod 5 is equal to 4. If you take 4 squared, that's 16 mod 5 is equal to 1. Now 4 cubed. 4 cubed is the same as 4 times 4 squared, and that's going to give you 4 again. 4 to the 4th, that's the same as 4 cubed times 4 to the 1st, that's 16, which gives me 1 again. 4, 1, 4, 1. So you can see that. Now, so you can see that for any even number, no matter how big, for any even number, the result is 1. So even if n is bigger than 1 million, then the answer is 1. Okay. All right. So how about the second one? For part B, what you need to use here is the fact that any multiplicative or additive factor in a modular expression can be replaced by its modular equivalent. So I'm going to replace 7654. I can replace that with its modular equivalent mod 10, which is 4, since it's equivalent mod 10. Okay, I can replace 20171 with 1, since it's equivalent mod 10. I can replace 345 with 5. And I can replace 678 with 8. Now, this only for the factors, not for the powers. You can't necessarily replace the powers with their modular equivalents. So how do you tell what that's going to be? Well, let's look at a mod of 4 to the 321, 10. Well, let's do the same thing. We'll take n and we'll do mod 4 to the n 10. So I'll take 1, 2, 3, 4, 5. So 4 to the 110 gives me 4. 4 squared gives me 16, which is 6. 4 cubed, well, cubed is 1 times 2, so 1 times 2 is 24, which gives me 4 again. So it looks like I'm getting this pattern 4, 6, 4, 6, 4, 6, 4, 6. Let's just make sure here. This would be so 6 times 6 is 36. Yes, so it's going to continue like that. All right. So what does that mean if I take 4 to the 321? Well, it looks like that's an odd number. The odd numbers give me 4. So that tells me that I'm going to get 4 for my answer here. All right. All right, let's go on and do the same thing for the next factor, which was 20171 to the 429. So 20171 to the 429. Now I remember I replaced 20141 with 1 to the 429. Okay, and that gives me 1. So that's that factor. Takes care of that factor. Let's go to the next factor. Next factor is 345. 345 to the 345. Well, remember, I can replace the 345 with 5 to the 345. And if you do this same sequence with 5, you'll notice that anytime you multiply 5 by itself, you're always going to get a number whose last decimal is 5, which means that that's always going to give you 5 no matter what. Okay. Then the last one is 678 to 678. Now 678 to 678. Remember, I can replace the 678 in the multiplication with 8, and I multiply that to the 678. And then if I do this n, and I do mod 8 to the n, 10, like that. If I just do the same thing, 1, 2, 3, 4, and I look at the pattern, all right, let's see, I'm going to get, well, 8 to the 1 is 8, 8 to the 2 is 8 times 8 is 64, gives me 4. 8 to the 3 is 8 times 4, which is 32, which gives me 2. And 8 to the 4 is going to be 8 times 2, gives me 6. 8 to the 5 is 2 times 3 is going to give me 8 again. You get this pattern. And you just have to see where does this fall in. Well, you can see that if it's a multiple of 4, you get 6. We know that 678 is not odd. If 678 is a multiple of 4, then we get 6. But it turns out that 678 is not a multiple of 4. It's a multiple of 2, but not a multiple of 4. That means that this applies. This 4 here applies. So that gives me 4. So my final expression reduces to, let's see what the expression was. First one was 6, 7. So this first factor here is 4. This one is 1. This one is 5. This one is 4 again. So that gives me 4 plus 1 times 5 plus 4, which is 13. And this is mod 10, so that takes it down to 3. I think that's right. All right, so that's how you do it. Remember, when you do modular arithmetic, the whole point is that you reduce your big numbers to small numbers within the modulus.